present here, distinguished guest.
Good morning, sir.
Good morning. Respected faculty members, dear participants and students. I warmly welcome to all in this 5 days online short-term training program on recent trends in sustainable development organized by Department of Basic Science, English and other core branches of Bengal College of Engineering and Technology, Durgapur. Myself, Abhijit Ghosh, head of the Department of Mathematics. In this session, our topic is geometry and sustainability. It is my pleasure to introduce our honorable speaker, Dr. Probir Rudro. He is assistant professor and head of the Department of Mathematics in Ashutosh College, Kolkata. He has more than 15 years experience as an educator of mathematics and over 10 years of experience as a researcher in gravity, relativity, cosmology, and astrophysics. He has awarded PhD degree from Indian Institute of Engineering, Science and Technology, SIPPU, and title of his thesis, Gravitational Collapse and Dynamics of some Dark Energy Models responsible for recent cosmic acceleration. He has over 100 research papers from reputed international journals. So, without further delay, I would like to invite Dr. Probir Rudro sir to share their insights. Hello, sir. Probir sir.
Can you hear me?
Yes, sir. Yes. Sir, now the session is over to you, sir.
Okay.
Thank you, sir.
Okay, fine.
Let's start.
Okay, so very good morning to all of you.
Good morning,
Can
sir.
you hear me?
Yes, sir.
Can you hear me? Thanks to the organizers for inviting me to this lecture. Thanks to sir for the introduction that he has given to me. Okay, so I can see that that we have around 34 students over here. Am I correct?
Yes, sir.
I can see 34 participants. Are all of them students?
Students and also some of them faculty members.
Okay. Okay. Okay, so I should start the session now.
Yes, sir. You may start, sir.
I should be sharing my slide. Okay. These students are from which year? These students are from first year or second year? Which year?
First year, second year. Maximum students comes from first year, second year, and
Okay.
few students are third year, fourth year also.
Okay. I see. So the students must be having some preliminary knowledge of geometry, I think. Students, can you confirm?
Yes, sir.
Most of you have studied geometry. Yes, in school.
Yes, sir.
Okay, so you can understand English properly?
Yes, sir.
Okay, so should I continue? Should I be continuing in English or should I move on to Bengali? Can you tell me? Is English okay for you?
We can continue with English.
Okay, okay, fine. Okay, so I should be continuing. Okay. Let me share the slide.
বলছি রয়্যাল এনফিল্ড কত পড়ছে নেবেন নাকি ভাব কি এটা ফেরত দিয়ে দেবো এক সপ্তাহ পুরো কমপ্লিট এই 163 অন রোড তারপরে পুজো দেবেন লোকজন খাবেন 100 লোকজন খাওয়ানোর ব্যাপার নেই
Thanks, Joy Kumar, for your response.
না লোক নেই জন আপনি ফিল্ড
Thank you, sir.
আমাদের খাওয়াবেন?
অবভিয়াসলি খাওয়াবো।
কোনো মতেই খাওয়াবেন না। একটা বিস্কুট খাইয়ে ছেড়ে দেবেন।
দেখতে পাবেন আমি এখানে আসার পর থেকে কিছু কিনেছি খাওয়ানোর মতো।
সে দেখবো।
বাড়ির গৃহপুরুষ।
Can you see my slide?
ঠিক আছে।
Yes, sir.
মাছ মাংস সব হবে কিন্তু আপনার জন্য পুরোপুরি নিরামিষ।
I think there are some interference over here.
দেখবো।
I cannot see the slide. Okay, let me switch off this video. Now it is okay. Can you see my slide now?
Yes, sir.
এটা মনে হচ্ছে আমাদের জোগাড় করে দিয়েছে। হ্যাঁ, নাহলে এদের ক্ষমতা নেই আসলে কলেজের লোক ধরা।
কে জোগাড় করে দিয়েছে?
Let me make it full screen.
হ্যাঁ দীপঙ্কর স্যার। সরি ঠিক আছে। হ্যাঁ মিউট করো।
Can you see now? I've made it full screen.
ঠিক আছে। হ্যাঁ ঠিক আছে। ঠিক আছে থ্যাংক ইউ। আপনি আছেন নাকি ঢুকে ওটাতে? এখন আর শোনা যাচ্ছে না তো?
Can you see the slide?
আপনার কি মিউট নেই?
Sir.
Yes, sir.
Can you see the full screen now?
Yes, sir.
Okay, so I should start now. Okay, the topic of my lecture is geometry and sustainability. Since the workshop is related to sustainability, okay, so I thought about it and I started realizing that mathematics, okay, do have a lot of relation with sustainability, and particularly geometry as a branch of mathematics, okay, do have a lot of connections with sustainability. Okay, so I've decided to choose this topic and go on with it. And geometry as a branch of mathematics, okay, does really have a lot of applications, okay, which is very important. And that is what I want to capture in this lecture of mine. Okay, so let's start this.
Respected faculty members, dear participants and students,
Just a
I
minute.
warmly welcome to all in this 5 days online short-term training program on recent trends in sustainable development organized by Department of Basic Science, English and other core branches of Bengal College of Engineering and Technology, Durgapur. Myself, Abhijit Ghosh, head of the Department of Mathematics. In this session, our topic is geometry
Okay,
and
so let us
sustainability.
get
It's
introduced to the
my
theme of the
pleasure
lecture.
to introduce
First
our
of all, you can
honorable
see
speaker,
that what is geometry?
Dr. Probir Rudro.
In school, you have studied geometry, all of
He is
you. I think.
assistant professor and
Probably
head of the
started in,
Department of Mathematics in Ashutosh
Standard
College,
5 or
Kolkata.
6. Okay, so what is
He has
geometry?
more than 15 years
All of us know
experience as an educator
that geometry is
of
basically the
mathematics
study of
and
shapes
over
and
10
patterns,
years of experience as a
different
researcher
structures,
in
and we also study the mathematical properties
gravity,
of it. Okay, that is the main part of geometry. Okay,
cosmology
geometry is not
and
merely
dynamics
shapes
of
and patterns,
light. Yes.
but actually the
Sir, now the
mathematical
session is over to
properties
you, sir.
of those shapes and patterns. Okay, that is
Okay.
what we study in
Thank you,
geometry. Okay, fine.
Let's
Okay,
start.
and what is sustainability? Sustainability is basically how we
That we have
use our
around 34
resources.
students over here.
On our
Am I
planet Earth, okay, we have got
Yes,
a lot
sir.
of resources.
I can see 34
And
participants.
sustainability is basically a process of using those resources properly. And we also have to protect our environment, which comes in sustainability. And we have to go for a long-term ecological balance, okay, to save us from getting extinct. Okay, that is what we mean by sustainability. We have to sustain ourselves and sustain the planet. Okay, when we sustain our planet, we sustain ourselves actually. actually. Okay, that is what we mean by the term sustainability. We have to live. Okay, we have to live, and in order to sustainability and mathematics is not so easy actually, because as we know that mathematics is a tool. Basically, mathematics is something what we do on paper. Okay, and sustainability is something which will look after the environment and all those things. Okay, so to find a connection between the two is not so easy. Okay, so let us see what we have here. Okay, so let us see some examples first. Okay, geometry in the environmental modeling first of all. Do anyone of you know what is fractals?
What you said, sir?
What is fractals? Can you tell me?
Vector is denoted which have magnitude and direction.
Not vectors. Fractals. You can see over here. Fractals, okay. Do you know what is a fractal? Fractals are basically very minute structures. Okay, they are very small minute structures. Okay, which are repeated over and over again to form a big structure. You can see over here. Okay, this is a flower basically. Okay, flower which are formed by the same type of structures. Okay, repeated again and again. You can see that we have these triangular leaves. Okay, small triangular leaves which are repeated over and over again to form this whole structure. Okay, this is what we call fractals. Okay, now fractals are geometrical shapes, okay, which are found widely in nature. Okay, they are found in coastlines. Okay, they are found in forests and cloud structures as well. Okay, they are used to describe the pollution dispersion and the river networks. Okay, so getting a good idea of fractals is very important to understand various ideas of environmentals. But then we have differential geometry. Differential geometry is basically a branch of geometry which is a very advanced form of geometry. And differential geometry deals with geometry which is not done on a flat surface. Okay, the geometry that you have done in school is basically geometry on a flat surface. Sorry. Okay, differential geometry is a geometry which is done on a curved surface. Okay, suppose the surface of a sphere, okay, that you can see over here. Okay, since the earth is not a flat surface, okay, so in order to understand the climate systems and the ocean currents, okay, we need to understand, okay, geometry of the curved surface. Okay, we need to understand the shape of the earth properly to understand the climate systems and the ocean currents. Okay, then we have the partial differential equations. Okay, I think you have this in your syllabus. Can you confirm? Partial differential equations, have you studied them in
It is including in the second year, sir. Partial differential equation.
Okay.
In what sense?
Okay. Yes. Okay, so in partial differential equations, okay, what we do is that we actually model the heat equations and we have the wave equations, okay, through which we can model the flow of water. We can also model the soil erosion. Okay, these are all environmental modeling actually. And using all this, we can do a climatic predictions. Okay, so you can understand how geometry actually helps us. How geometry helps us to understand the climatic procedures, okay, how nature works at that level. Okay, then we have geometry in urban planning as well. Okay, first of all, you can see that we have these hospitals, okay, and we have to place these hospitals at distances, okay, which are comfortable for the people to reach. Okay, to do that, we use this geometrical diagrams, okay, known as the Voronoi diagrams, and we space the hospitals in such a way that it becomes much more convenient for the people to use. Okay, similarly, for the water points and for the green spaces, we use these diagrams. You can see the diagrams over here. Okay, the points over here actually represent those water points or the hospitals, okay, which are spaced in such a way that people can actually reach them or use them at convenience. Okay, so these are what we know as the Voronoi diagrams. Okay, and they are used in the city planning actually. And then we have the graph theory and the network geometry. They are used for the transportation layouts. Okay, and we have the isometric mapping and GIS as well, which are used for the land planning. Okay, and for the land planning means, I want to say, say you want to allocate lands to the people for building homes. Okay, or you can allocate lands for the people for cultivation. Okay, all those things are there. Okay, for these things also we need a proper knowledge of geometry. And what is the impact of this? Okay, they reduce the travel distances, obviously. Okay, when we plan properly, okay, that gives us some output as well. Okay, they reduce our travel distances, our travel time, and the use of the force and the energy, and improves actually the quality of life, isn't it? Okay. Then we have the use of geometry in sustainable agriculture. Okay, you can see over here, okay, this is what we know as the contour farming. Contour farming is basically a geometric modeling of land curves. Okay, we use these lands properly, and we use them for cultivation in such a way that we use an optimum, that we get an optimum use of the land available to us. That is what we know as the contour farming. And then we have got this triangular planting patterns, okay, that you can see over here. Triangular planting patterns actually optimize the nutrient distribution of the plants and the sunlight exposure. All these are applications of shapes and geometries. Okay, finally we have this geospatial geometry, okay, which are used in the precision agriculture. And the impact is that obviously that increases the crop yield. Okay, since we have a population boom nowadays, we need to feed teeming millions. Okay, and that is why we need to increase our crop yield. Okay, that is what we do using geometry. Okay, now we come to the mathematical part of this. Okay, which is the most important part of this lecture. Okay, geometry, as you have studied in school, is known as the Euclidean geometry. Okay, the geometry that was devised or that was proposed by Euclid. Who was it? Can you tell me who was Euclid? Do you have any idea? Somebody from you, can you tell me who was Euclid? Okay, Euclid was basically a Greek mathematician, mainly a geometer who actually devised the earliest form of geometry that you have studied in school. Okay, the geometry that you have studied in school is basically lines and angles geometry. Okay, that is what you have studied. Okay, Euclidean geometry basically means the shapes and the figures that we draw on a flat surface. And you can see over here, okay, the first diagram over here. You can see that this is a flat surface and we can draw various shapes Okay, that is what you have done in school, isn't it? You have drawn the shapes on the sheet of paper, okay, which is flat. That is called Euclidean geometry. But that is not the final form of geometry, or that is not the all of geometry. Okay, we also have a non-Euclidean form of geometry. Okay, non-Euclidean form of geometry is actually geometry that we do on a non-flat surface. Okay, non-flat surface, by non-flat surface I mean surfaces like this, okay, which is a spherical surface, okay, which is not a flat surface obviously, and we have this hyperbolic surface as well, something like a saddle. Okay, all these two are basically non-flat surfaces. The first one, which is the spherical surface, do have a positive curvature, okay, and the next one, which is the hyperbolic surface, so we do have a negative curvature. What is curvature? Can you tell me what is curvature? Sorry. Do you have any idea what is curvature?
Anyone from the students? Sir, ask some question. Please reply if you know about it.
Okay, I think most of you have started calculus.
Yes, sir.
Okay, so in calculus, okay, we have this curvature. Okay, we can find out the curvature of curves. Okay, by using derivatives. Okay, we use derivatives to find out the curvature of a curve. Okay, when the curve, but over here, okay, what we do is that we are having a curved surface. Okay, not a curve. This is a curved surface. Okay, and we are very much interested in finding out the curvature of that surface. Okay, so for a sphere, we can understand that it has a positive curvature, and for the hyperbolic surface, we have a negative curvature. Okay, something in the form of a saddle of a horse, isn't it? Okay, all these forms actually come under the non-Euclidean geometry. Okay, let's take a very good example. Okay, suppose you want to draw a triangle. Okay, suppose you have got these three forms of surfaces, and you want to draw a triangle on these three surfaces. Okay, this is the Euclidean surface, okay, the middle one, okay, which is a flat surface, and you draw a triangle, okay, which you have done many times before also. Okay, and we know that the sum of the angles of the triangle is actually 180 degrees, okay, that you can see over here. Okay, angle alpha plus beta plus gamma is 180 degrees. Okay, that is what we have on a flat surface, okay, the Euclidean surface. Okay, but when we draw this triangle on this sphere or on this saddle-like surface, okay, you can see that the angle is no longer summing up to 180 degrees. Okay, you can see that the sum of the angles for the sphere is actually more than 180 degrees over here, and for this triangle on the saddle, okay, the angle is actually less than 180 degrees. So you can see that the basic property of triangle that you have drawn on a flat surface does not hold, okay, for the non-flat surface. Okay, this is a good motivation for studying non-Euclidean forms of geometry as well. Okay, so the geometry that we do on these non-flat surfaces, okay, that is called the non-Euclidean geometry. Okay, so let us move forward and see what we have. Okay, so first of all, let us know something about Euclid. Okay, who was Euclid? Euclid was basically a Greek mathematician. Okay, the time is around 325 BC, which will be around 2500 years back. Okay, that is a long time back. And he studied at Plato's Academy, and he worked actively on mathematics and then optics and astronomy, music and mechanics. And he wrote this book called the Euclid's Elements. Okay, that is his major contribution to mathematics. There are 13 volumes in all, and they involve basically plane geometry, solid geometry, and number theory. Okay, so basically Euclid uses the axiomatic method, okay, to develop the geometry that he has done. Okay, what do you mean by axioms? Can you tell me what is axioms? You have actually studied this in school. What are axioms? So axioms are something, okay, for which we do not demand any proof. Okay, axioms are some rules, okay, which are taken for granted that they are true. Okay, which are so obvious, okay, that we do not demand any proof. Okay, these are called axioms. Okay, let us see. Okay, so what is the axiomatic method? Okay, we start with some unproved assumptions, okay, which are known as the axioms or postulates, and then we use some logic, okay, and go forward, and we form some results, okay, based on these axioms. Okay, these are the two basic ideas of the axiomatic method. Okay, we take some assumptions, okay, which are not proved, okay, and we use logic from there, and we establish, okay, some results. Okay, this is the axiomatic method. Okay. Okay, now the whole of Euclidean geometry is based on some postulates or axioms. Okay, there are 5 axioms of Euclid, okay, which we have actually studied in I think standard 5 or 6 that you have studied. Okay, when you first started geometry, okay, there were 5 axioms of Euclid, and the whole of Euclidean geometry actually stands on these 5 axioms. Okay, here I have listed the first 4 of the axioms, okay, which are very, very obvious, and we do not need any proof of them, basically. Okay, so the first axiom is that we can draw a straight line from one point to another point. Okay, do we need any proof for this? Okay, we do not. Okay, this is so obvious. We have got 2 points. We can draw a straight line from one point to another point. Okay, that is so obvious. The second axiom is that we can actually produce a finite straight line continuously. Okay, we have got a straight line and we can produce the straight line. Okay, that is the second axiom, which is also very, very obvious. The third axiom is that we can describe a circle with any center and distance. Okay, suppose you are given a point as the center of the circle, and you are given a distance as the radius of the circle. We can always draw a circle, isn't it? Okay, when we are given the center of the circle and we are given the radius, okay, we can always draw the circle, isn't it? Okay, so which is very, very obvious. The fourth axiom is that all right angles are same. They are all equal to one another. Okay, suppose you draw 2 right angles on the page of a paper. Okay, on the paper you draw 2 right angles. Okay, and then you measure the 2 right angles. Okay, say with a protractor, you will find that both the right angles are equal to 90 degrees. Okay, so these are the first 4 axioms, okay, which are very, very simple and very, very obvious. Now we come to the 5th postulate of Euclid, okay, which is the main turning point of Euclidean geometry. Okay, the statement is here. Okay, so if a straight line falling on 2 straight lines make the interior angles on the same side, okay, less than 2 right angles, the 2 straight lines, when produced indefinitely, meet on the side in which the angles are less than 2 right angles. Okay, the postulate, as it seems to be very, very complicated, isn't it? Okay, so we need to see the figure first, okay, to understand what has been said over here. Okay, so what is it? Okay, you can see that I have drawn 2 blue lines over here. Okay, these are the 2 straight lines, okay, the blue lines, okay, that I have drawn over here. And this red line actually cuts the two straight lines. Okay, and I've drawn these two angles over here. Okay, the alpha angle and beta angle. Okay, the statement of the fifth postulate actually says that if alpha plus beta is less than 180 degrees, then the blue lines will cut on the right side of the red line. Okay, this is the red line and this is the right side of the red line. Okay. If alpha plus beta is less than 180 degrees, okay, then the blue lines will actually cut on this side, okay, the right side of the red line. And if alpha plus beta is greater than 180 degree, then the blue lines will actually cut on the left side, okay, the left side of the red line. This is the Euclid's fifth postulate, and they have got many equivalent statement as well. Okay, so you can see that the fifth postulate is quite different from the first four. Okay, first of all, the fifth postulate is not so obvious and not so simple as the first four. You can see that the first four postulates are so simple and so easy. Okay, the fifth postulate is so complicated, the statement is very complicated. Okay, so the first four are physically verifiable. Okay, they are very easily verifiable with the help of a pencil, a ruler, a compass, and a protractor. Okay, you can use your geometry box and physically verify the first four postulates very easily, isn't it? Okay, now, since the fifth postulate is so complicated, okay, what we do is that we have an idea. Okay, the idea is that, okay, why don't we try to prove the fifth postulate from the first four? Okay, we use the first four postulates and try to prove the fifth postulate. Okay, and if we can do that, we do not need the fifth postulate anymore. We can just remove it. Okay, that will actually simplify the system much more. Okay, we will use the first four and try to prove the fifth postulate. And if we succeed, we will just remove the fifth postulate. And our system is very simple now. Okay, so this is the idea that the mathematicians got at that time. Okay, they wanted to prove the fifth postulate from the first four, and just they wanted to remove the fifth postulate to simplify the system. Okay, do you understand? Can you hear me? Can you hear me?
Yes, sir.
Okay.
Yes, sir.
Okay. Are you understanding what I am saying actually? Are you enjoying the lecture?
Yes, sir. Yes, sir.
Okay. Okay, so the mathematicians, okay, they started to prove the fifth postulate, okay, using the first four. And the first one was named Proclus, okay, for around 5th century AD. He tried to prove the fifth postulate using the first four. Proclus was actually a critic who wrote a commentary on Euclid, and he tried to prove the fifth postulate, okay, by using some geometrical constructions. Okay, but the problem was that Proclus actually failed. Okay, Proclus actually could not prove the fifth postulate, okay, using the first four. Then came the man known as the Girolamo Saccheri, okay, in the 17th century. He was actually a Jesuit priest, and he taught in a Jesuit college of Turin. And he was a very big fan of Euclid, and he wrote this book also, the Euclid Freed from Every Flaw. Okay, so you can understand that he wanted to remove all the tarnished, okay, from Euclid, and he wanted to prove the Euclidean geometry correct actually. So he tried to prove the fifth postulate, okay, using the first four, and he wrote a book on that as well. Okay, but the proof that he gave, okay, was not correct at all. Okay, that was also not correct. Okay, so in total, at that time, okay, probably it was around, let's say 4th century AD to around, I think it will be around 7th to 8th century AD. Okay, there were different mathematicians, okay, who tried to prove that fifth postulate, okay, using the first four. And they were actually found to be 28 different proofs, okay, which were all wrong actually. They were not correct at all, but there were 24 different attempts, okay, to prove the fifth postulate of Euclid using the first four postulate. And G.S. Kugel actually wrote a doctoral thesis on this. Okay, he analyzed all those 28 different attempts which were not correct actually. Okay, and he wrote a thesis on that. Okay, so you can see that all the mathematicians who were so fond of Euclid, okay, so they were fan of Euclid, and they were all working to prove Euclid correct. Okay, but the main thing to note was that all these proofs, okay, that these mathematicians gave were all direct proofs. Okay, these were all direct proofs. Okay, they wanted to prove the fifth postulate directly from the first four postulates. Okay, this is where the mathematicians actually got wrong. Okay, then came this man, okay, known as Janos Bolyai, and he wanted to prove the fifth postulate using the first four. Okay, this is actually a modern proof. Okay, you can see the time over here. Okay, this is actually a modern proof, almost the 19th century. Okay, and he wanted to prove the fifth postulate by the method of contradiction, not by the direct method as the previous mathematicians did. He wanted to prove this by the method of contradictions. Okay, so what is the method of contradiction? Okay. The first step is that we assume the result, okay, that that we want to prove as false. Okay, means we want to prove the fifth postulate. Okay, so in the beginning, we assume that the fifth postulate is false. Okay, that is not correct. Okay, then using the initial assumption, okay, we reach a contradiction. Okay, the step 2 is that we reach a contradiction. Okay, and finally we conclude that the initial assumption, okay, that we considered was not correct. Okay, so I sum up the whole thing. Okay, we take okay, the final result, okay, that we want to prove. Okay, we take that as false. Okay, then we use some mathematical logic and we arrive at a contradiction. Contradiction means something which is not mathematically correct. And from that contradiction, we conclude that the initial guess that we did, that was wrong. Okay, so we can say that the final thing, okay, that we took as false is actually true. Okay, this is proof by contradiction. Okay, this is actually a logical procedure, and we study this in mathematical logic. Okay, so what we did is this: to prove by the mathematical to prove the fifth postulate by using contradiction. Okay, first of all, what we do is that we use an alternative statement for the fifth postulate. Okay, so the alternative statement is that a line is given L. Okay, this is the line L which is given. Okay, and we have a point P as well, which is not on the line. Okay, this is the point P. This is the point P which is not on the line. Okay, and it says that there exists a unique line through P parallel to L. Okay, that means through P we can draw a unique line. Okay, unique line means one and only one line through P and parallel to the line L. This is an alternative statement of the fifth postulate of Euclid. Okay. So Bolyai started with the negation of the fifth postulate. Okay, I told you that we will start with the negation of the result, okay, that we want to reach. Okay, we will consider that the final result is wrong. Okay, so he considered that given a line and a point P, okay, line is there and point P is over here, not on the line. Okay, we have got two different options. First one is that there exists more than one line passing through P parallel to L. Okay, the first diagram. Okay, through P we have got more than one line passing through P and parallel to L. And the second one is that there are no lines which are parallel to L and passing through P. Okay, so you can see the previous slide. Okay, the statement actually says that there exists a unique line passing through P and parallel to L. This is the statement. This is the fifth postulate. Okay, the negation of this will be actually that there can be more than one line passing through P, or there can be no lines passing through P parallel to L. Okay. So these two different assumptions actually lead us to two different forms of geometry that we will see later. Okay, and Bolyai reached a complete list of contradictions. Okay, so he started with these wrong assumptions. Okay, these two wrong assumptions. Okay, and he used some mathematical logic, and he wanted to reach some contradictions. Okay, so if we reach some contradictions, we can say that these guesses were wrong, and this is correct, and this is correct. Okay, and so the fifth postulate will be proved correct, isn't it? Okay, so he started with these wrong statements. Okay, these counter examples, okay, the counter statements, and he wanted to reach some contradictions. Okay, so these are the complete list of contradictions, okay, that he reached, and you can see that the list is empty. Okay, there are no contradictions, okay, that he reached. Bolyai actually did not reach to any contradictions by assuming these two guesses. Okay, so when we do not reach any contradictions, okay, by the initial guess, so what do we say that? Okay, what does that mean actually? Okay, when we assume something and do some mathematical methods and reach somewhere, okay, which is not some contradictions, okay, which are mathematically correct. Okay, so in that case, okay, we can see that these guesses were not wrong actually. Okay, since we do not reach any contradictions, okay, we can actually conclude that these guesses of Bolyai, which he actually thought to be wrong, okay, were not actually wrong. Okay, so Bolyai said that out of nothing I have created a strange universe. Okay, so Bolyai actually expected to reach some mathematical contradictions. Okay, so that he can say that his initial guesses were wrong and Euclid was correct, but he did not reach any contradictions. Okay, so Bolyai understood that he has actually reached someplace new. He has actually created a strange new universe, a new form of geometry, which does not follow the Euclid's axioms, non-Euclidean geometry that we will see. Okay, Gauss was there. I think most of you have learnt about Gauss. Can you confirm? Do you know the name Gauss?
Yes, sir.
Okay, so Gauss was actually a mathematician, an 18th century mathematician, and Gauss actually had a connection with Bolyai's father. Okay, and Bolyai actually and Bolyai's father actually wanted Bolyai to be a pupil of Gauss, but Gauss was not interested to take Bolyai as his student as well. Okay, so when his father, Bolyai's father, actually took the work of took the work of Bolyai and presented it to Gauss. And when Gauss saw Bolyai's work, he said that these results were actually proven by me more than 35 years back. Okay, and he did not publish them. Okay, he actually proved them 35 years back, but he did not publish them. Okay, so actually Gauss wanted to take the credit of what Bolyai did actually. Okay, then we come to this man, Lobachevsky, who was a Russian mathematician. Okay, he actually developed many ideas of non-Euclidean geometry and published all his results in Russian. Okay, these three people that I have named, the first one is Bolyai, okay, the second one is Gauss, and the third one is this Lobachevsky. These are the three people who actually developed the non-Euclidean geometry. These are the three people who actually understood the flaws of the fifth postulate of Euclid and also understood that we can have different avenues to Euclidean geometry, okay, which will not support the fifth postulate, and those avenues will actually lead to geometry on curved surfaces. Okay, these are actually non-Euclidean geometries, and these three peoples are credited for the development of the non-Euclidean geometry that we study in modern mathematics. Okay, so in non-Euclidean geometry, you can see that we can have two different forms. Okay, the first one is the hyperbolic geometry, where the sum of the triangles, the sum of the angles of the triangles, okay, does not sum up to 180 degrees, but they are less than 180 degrees. Okay, that I've shown you before as well. Okay, we draw a triangle on this surface, and you can see that when we add the angles of these triangles, okay, they will be less than 180 degree. Okay, the curvature is negative for this surface. Okay, the curvature is actually negative for this surface. We have a flat surface. The flat surface, for the flat surface, the curvature is 0. Okay, the sheet of paper, the flat sheet of paper where you draw the triangle, the curvature of that flat sheet is 0 actually. Okay, no curvature means 0 curvature. Okay, and for this surface, where the sum of the angles of the triangle is less than 180 degree, okay, the curvature is negative. Okay, this comes from the first assumption of Bolyai. Okay. This was the first assumption. Okay, this was the first assumption. This was the first assumption. Okay, where he took that there can be more than one lines parallel to the straight line passing through P. From this first assumption, we have the hyperbolic geometry, and from this second assumption, where Bolyai took that there are no straight lines passing through P and parallel to L. Okay, from here we have a new form of geometry known as the spherical geometry. Okay, okay, so from the first assumption, we have this hyperbolic geometry. You can see that more than one parallel line passing through P, curvature is negative, and the triangles, the sum of the angles sum up to less than 180 degrees. And we have the elliptic geometry. Okay, the elliptic geometry from the second case where no parallel lines are passing through P. Okay, this one. Okay, this is it. This is the second one. Okay, this is the second one where we took that there are no parallel lines passing through P parallel to L. And from the second assumption of Bolyai, we have a new avenue of geometry known as the elliptic geometry. Okay, for this surface, the curvature is positive, you can see, and the sum of the angles of the triangle, they add up to more than 180 degrees. Okay, this is the elliptic geometry. Okay, both this hyperbolic geometry and the elliptic geometry are branches of the differential geometry that we study nowadays. Okay, we have a branch known as the differential geometry where we use calculus in geometry. Okay, and these two forms of geometry actually make up the differential geometry. Okay, now finally we move towards a big question. Okay, both these forms of non-Euclidean geometries, okay, both these are non-Euclidean geometries, okay, that we do on curved surfaces. both these types of non-Euclidean geometries are self-consistent. What do you mean by self-consistent? Self-consistent means that they are true. Okay, there is nothing wrong with these geometries. We also know that the Euclidean geometry that we did in school, okay, they are also self-consistent. Okay, the non-Euclidean geometry is self-consistent, and the Euclidean geometry is also self-consistent. Both these forms of geometry are correct. Okay, and we also see that all these forms of geometries are mutually exclusive. Can you tell me what is the meaning of mutually exclusive? Did you study probability?
That means there is no common space.
Yes. Okay, so there is no intersection between them. Okay. Okay. So all these forms of geometry, both the Euclidean and the non-Euclidean form, okay, there is no common part. Okay, all these are mutually exclusive. These are separate forms of geometries, and we cannot have a space, okay, that is both Euclidean and non-Euclidean. Okay, that is what we mean by mutually exclusive. Okay, there is no space which can be both Euclidean and non-Euclidean at the same time. Isn't it? Either a space will be Euclidean or it will be non-Euclidean. Okay, a space cannot be both Euclidean and non-Euclidean at the same time. Okay, so you can see that both these forms of geometries are correct, and they are mutually exclusive as well. Okay, so we come to the big question. Okay, the big question is that which one of these geometries are correct actually? Is non-Euclidean geometry correct? Non-Euclidean geometry, we have got two parts, okay, the hyperbolic geometry and the elliptic geometry, and we also have the Euclidean geometry as well. Which of these three geometries are correct? And which of these three geometries actually represent the universe as we know it? When we think about the universe, you can see that basically we have got so many problems in our earthly lives, in our terrestrial life, okay, we forget to think about the universe. Okay, our universe actually houses all these planets and the stars and the galaxies. Okay, the universe is actually the bigger picture, and we actually forget to think about the universe, and we become so self-centered that we only think about our lives and we think about our planet. Okay, but when we go beyond this thinking, beyond this realm of thinking, we understand that beyond this earth also we have a big space, and we actually have to think about our universe to sustain ourselves. Okay, since the theme of this talk is sustainability, I should say this: we have to think about the universe to sustain ourselves. Okay, I'll tell that in detail later. Okay, so the question is now that which of the three geometries actually represent the universe? Our universe is actually of zero curvature or positive curvature or negative curvature. Okay, is it flat or is it elliptical or hyperbolic? This is the big question that we come to. Okay, so we have this WMAP survey, the Wilkinson Microwave Anisotropy Probe. Okay, this is a part of cosmology, okay, which you may not know. Okay, this is actually an experiment to understand the universe, and it was launched in 2001 by NASA. And what it does is that it actually tells us, it takes data. Okay, actually it takes data, and from that data we can actually tell us we can actually tell about the nature of space. Okay, means the nature of the universe. Okay, the nature of the geometry of the universe. Okay, what is the geometry of the universe? By geometry I mean a universe will be a Euclidean or non-Euclidean. That is what the data from the WMAP survey actually tells us. And also we have this CMB, the cosmic microwave background. These are all cosmological experiments. Okay, and cosmology actually means the study of the universe. Okay, cosmology, the branch of cosmology, actually means the study of the universe. And the data from all these cosmological experiments actually shows us that the curvature of the universe is actually this. Okay, when we minus 0.0027 and with the error limit of plus 0.0039 and minus 0.0038, and the range actually becomes this, minus 0.0065 to plus 0.0012. This is actually the curvature of the universe that we get from the data of those experiments. Okay, so you can see that the curvature of the universe is pretty close to that zero mark. Okay, you can see that the curvature of the universe is very, very close to the zero mark. And the zero mark and zero curvature actually means what? Means that the universe
It's
is
flat.
yes. Hello?
That means the universe is flat.
Yes, yes. Okay, so it says that when we see that the curvature of the universe is closer to zero, this means that the best guess, okay, we are not sure about this, okay, because the data is coming from the experiments, and experiments can always be refined more and more to get better results. Okay, so the data may not be totally reliable for the time being. Maybe in future we will have better data as well. Okay, so at the time being we can say that the best guess from the data that we are getting is that the universe is probably Euclidean. Okay, the space, the universe is actually flat, and flat means the Euclidean geometry is basically the geometry that is followed by the nature, by the universe. Okay, now we come to the final part of this lecture, that how is geometry actually related to sustainability, the sustainability of humanity, the sustainability of the future of humanity. How is geometry related to human being and our future? You can see in these pictures, okay, these are very, very sorry pictures, okay, that I've collected from Google. You can see that the first picture is of deforestation. This is a pollution. Okay, these two are pollutions. Okay, this is plastic pollution. Okay, this is a global warming. This is a melting of the ice caps, and this is tsunami. Okay, all these are very, very sorry pictures. Okay, that is happening to our earth now. Okay, and who are responsible for this? Okay, we the human beings are actually responsible for this. We are continuously destroying our mother earth, okay, by our acts, by our greed. Day by day we are harvesting the resources from the earth. We are doing mining, we are doing over mining. Okay, we are actually polluting the environments. Okay, we are cutting down the trees. Okay, and all these are actually leading to global warming, and we are destroying the nature. Okay, we can see that when we have global warming, the polar caps will melt and the sea levels will rise, and many of the land, okay, that we can see now will be covered by the oceans. Okay, when we have lesser land to live and more population will be there, okay, how will we sustain ourselves? How will we live? Okay, when we have so much pollution, okay, what will we breathe? Okay, so these are big questions that we have to address. There are destructions all around, okay, that is for sure. Okay, so you can see that when we have so much destructions all around, and when we are ourselves doing that, okay, probably someday in future, maybe in near future, okay, we will lose our Earth. Okay, we will not be able to save the Earth, which is the only home in the universe. Okay, in the whole universe, okay, we haven't yet found a single planet which can support life, except Earth. So what we can see over here is that probably if we go on in this way, and if we do not rectify ourselves, okay, we will lose our Earth. And that will lead to the extinction of humanity as well. Okay, when we do not have Earth, when we do not have a home to live, we will definitely go extinct. Okay, man cannot live without Earth, isn't it? Man cannot live on Mars, man cannot live on Venus. Okay, none of the planets in the solar system support life. Okay, so what we can do actually, there are basically two options for us. Okay, for this, to avoid this inevitable future, okay, which is a very, very dark future for us, we have got these two options for us. The first one is that we can either protect our environment and thus protect ourselves from getting extinct, which is very, very highly unlikely to happen because day by day the population is increasing, and we are getting more more and more greedy. We will continue to do more and more mining. We will continue to cut our forests down for resources. Okay, all these things will continue to happen. Okay, if the populations become more and more, to feed the teeming millions, we need more and more resources. And where will we get the resources from? We will have to harvest it from the earth. So it is very, very difficult for ourselves to protect our environment with that mindset. So what is the second option? Okay, let us see the second option. Okay, so when we cannot save our home, okay, and if we ultimately destroy our home, okay, when we cannot save our own home from getting destroyed, the only option that remains is that we will have to find a new home for us. And a new home means that we will have to find a new planet that supports life. A planet that is habitable, a planet somewhere in the stars, a planet that is somewhere in the stars, and to find that new home, we will need to understand the universe. We will need to do a lot of space travel. Agencies like NASA, agencies like ISRO, all these agencies have to come together and do a lot of research, do a lot of astronomical research. We have to know a lot about the universe to find a new home. Do you know that the closest star from us, okay, leaving out sun, the closest star from the Earth is actually Proxima Centauri, and it is situated at a distance of 4.2 light years. And with the current technology, with the space rockets that we have now, we will take around 50,000 to 60,000 years to reach the nearest star. Okay, so that is a time which is not imaginable. 50,000 years, okay, nobody will be alive. Our biological system does not support interstellar travel, then how will we find the new planet? That is a big question. Okay, but we have got these two questions. Okay, these two options for us only. Either we save our environment or we find a new home. Okay, now we come to the final slide for us. To understand our universe, we need to have a good idea of gravity, because everything around us, everything that the universe beholds, is actually bound by a unifying force known as gravity. And we know that the first form of gravity, the first theory of gravity, was given by Isaac Newton in the 17th century, but that is not the modern theory of gravity. Okay, we teach the Newtonian gravity in school, obviously, but that theory is not the modern theory. Now we have a modern theory of gravity which was given by Einstein, known as the general theory of relativity. And that theory, the general theory of relativity, is basically completely a geometric theory. The total theory is based on geometry. Okay, and if we have a good understanding of this general theory of gravity, we will understand how gravity works at that large scale, and that is how we will be understanding. We'll have a good idea about the universe, and after we have a good idea of the universe, we can do our space travel and find a new home for us. So you can see that the future of humanity is actually dependent on this branch of mathematics, which is geometry. So in order to sustain ourselves, we need to have a good idea of geometry, and that is how we relate geometry to sustainability. Both our terrestrial and the extraterrestrial future depends on a complete knowledge of geometry. Thank you very much. Okay, thank you very much for listening. I hope you have understood the lecture. And now if you have any question, you can ask me.
Anybody having any question or any doubt? So please ask to Pavit sir.
Sir, myself, Vivekananda here, faculty member of Department of Mathematics of PCET. Sir, I would like to know from you that from experimental data of universe, you can say that universe is flat. It is okay, but it is true in totality, or it is just true for very two small distances on the surfaces?
No, at the local level, okay, means at the shorter distances, means at the local level, okay, the universe is not flat. Okay, I mean at the larger distances, at the large scale only, the universe is flat.
Okay, sir. Thank you, sir.
Yes.
Anyone? Anyone else? Anybody having any queries? Please
No,
ask.
sir.
Yes, please ask your question. Yes.
I asking you another question that if there is any case when we assume that if Euclidean geometry and non-Euclidean geometry are same,
Yes.
is there any case?
I did not get you.
That means,
Please, can you repeat?
That means, can we say if there is any state that where I'm supposed to be that the Euclidean geometry and non-Euclidean geometry are same?
The voice is breaking actually. I cannot hear. Please, can you repeat?
Actually, there are network problem. Vivekananda,
Yes.
kindly repeat.
Sir, am I audible now, sir?
Yes.
Sound is not clear.
Can you
I
write the
actually
question
don't
on the chat box? Chat box. Please write the question on the chat box.
Yes, yes. Any doubt? Write the chat box. Use the chat box, please.
Okay. So it seems that most of them have understood the lecture, I think. Can you give any feedback on the lecture? Just can you give any feedback on the lecture? That how
Yes,
much you
sir.
enjoyed the lecture? Can you tell me? The students, can you tell me, please? That did you enjoy the lecture? Did you understand the lecture?
Students, if you want to tell anything to any feedback to Pavit
Somebody
sir,
from you?
please tell.
Somebody from you? Please tell me.
Yes, sir. They have reply in chat box, sir.
Okay, that is very good.
Hmm.
Okay, so the idea is basically to make the students understand, okay, because this is so much geometry is so much having connection with this sustainability thing. Okay, so it is very important to have a knowledge of geometry to understand the universe and to take humanity forward, isn't it? Okay, geometry has got much more applications, okay, than the other branches of mathematics, and that is why I decided to choose this.
Yes, a student give the message.
Yes,
Many
I've
students.
seen.
Many students.
Okay, very good session. So,
Yes.
okay, thank you very much. Okay, the main idea is to make you understand. Okay, so if you have understood the lectures, okay, that is good for me. Okay, so we don't think that we have any more questions. Okay, they say that that the lecture was good. Okay, thank you very much.
Okay, I think nobody having any queries or any doubt. But I must say thanks to Pavit sir to use such a important topic in the basis of our present situation. And I believe this session will greatly benefit to all the students and faculty members. And once again, thank you, Pavit sir, for give us such a nice presentation. So thank you, sir. Thank you very much.
Thank you very much. Okay, thank you very much for inviting me to this lecture.
Yes, sir.
Okay, thank you so much.
Thank you, sir. Thank you.
Thanks to the audience for listening to me. Okay.
Thanks to all the participants. Thank you, Pavit sir, once again. And
okay, so
now,
should I leave the meeting now?
Yes, sir. Yes, sir.
Okay. Thank you very much.
Okay. Thank you.
And
sir.
goodbye to all of you.